Yeah, hello there. So this is the first video about chemical reaction engineering and reactor technology. So this is the first topic we're going to talk about, which is gas-liquid reactions. So basically what we can see here is that components in the gas phase diffuse to the gas-liquid interface, and they dissolve in the liquid phase and react with components in the bulk liquid phase. So basically that's what is going on here with A. Let me change the color. Probably I'm going to use maybe a red colored, and this is what I just described. So the component in the gas bulk is diffusing through the gas film and is going to be absorbed in the liquid film. Okay, so we can see this jump here because they have different units. So I'm going to explain this later on, but this discontinuity is just because of different units. Here we are using pascals or bars, and here we're using concentration, units of concentration like molar or molal. And in the liquid phase may also contain. So in this phase we could have a homogeneous catalyst, and some of the product's molecules dissolve from the liquid phase to the gas phase. So this is what we are seeing here, that P is the product and it's dissolving from the liquid phase to the gas phase. Okay. What else? And some molecules remained in the liquid. So these kind of reactions in the gas-liquid reactions are very common in industry. For instance, the absorption of nitrogen dioxide in water in the production of HNO3, or the absorption of carbon dioxide in sodium hydroxide or potassium hydroxide as well. There are many examples of this kind of systems. For instance, the absorption of CO2 in amine solutions. This is very common when we want, for instance, to remove CO2 or sulfur hydroxide. Oh, sorry, this is hydroxide. Sulfuric, let's say sulfuric acid or sulfur hydroxide. No, this is not sulfur hydroxide. This is sorry. What I mean is hydrogen sulfide, of course, which is not the one here. I have the same color, but it's not the one that I have here in this system. This kind of systems of gas-liquid reactions are very common in industry, and that's why we are interested in studying them and understanding the principle behind this. There are different reactors for these, and we will see that later on, but there are mainly two types of reactors. So the tank and the bubble column. The tank reactor is good for it has good mixing capability, and it's good for highly exothermic reactions or highly viscous liquids, so mainly non-Newtonian liquids. And when we talk about plate versus packed columns, so when we decide that we are going for maximizing the surface area, meaning that the system is mass limited, then one of the options we have is plates or packed columns. So the main difference between them, let me show you them. So here we have different types of reactors that we can use, or absorbers. Sometimes they're called absorbers, depends if they have only physical absorption or chemical absorption as well. So we are interested in the chemical one when we have chemical absorption as well, right? So one of the options, as I told you, is the difference between plate columns and packed columns. And so when you are going to decide which of them you need to use, there are many factors to take into account, but let's say 5 of the factors you need to look into are the pressure drop. So the pressure drop in the packed column is usually lower than in the plate columns, and for diameters less than 1 meter, packed columns are cheaper in operation and in as well in the in the built up let's say capital cost and capital cost. So the flow conditions are easier to control in plate column, and plate column is suitable for reactions that occurred in the liquid bulk. So basically, if you want to maximize, or if you have a mass limited system, you're going for packed columns, but if you have a kinetic limited system, it's better if you have plate columns. And yeah, so one problem you could face with packed columns is the short circuiting of the flow of gas. So slow reactions go for bubble column, and fast reactions go for scrubber or spray towers. So again, if you have slow reactions, that means you want to, so you are kinetic limited, so you need a high hold up. That means it doesn't matter if you have a high interfacial area. So that's something that I mentioned already in the videos of conceptual design when I was designing one of these reactors for one specific problem. But yes, you can give a look to that problem. And now we are going to do the mass balance for a ideal gas liquid reactor. So let's keep in mind this image because somehow it's going to disappear while we are working on the problem. Okay, so basically we are going to do the balance first in the liquid bulk. So in the liquid part, let's say taking into account the liquid film and the liquid bulk. Okay, so we are going to say that the flux that comes in plus whatever comes from the bulk, so NLIB, right, delta of A, which is this interfacial area right here, plus whatever reacts, delta of volume of the liquid is going to be equal to what leaves. Makes sense, right? Whatever comes here plus whatever comes here plus whatever appears here or disappears is going to be equal to whatever leaves here. And now we can use the hold up of the liquid. We're going to say, okay, hold up of liquid is going to be, of course, the delta of volume of liquid over the let's say just the volume of the reactor. And we are using deltas because this is a differential differential element that we are taking into account. And then if we say, okay, let's say that another ratio here is going to be the area over the total volume, which is the ratio of interfacial area to reactor volume. And then we use these and we plugged all of these two expressions or ratios here in the expression we have, and we are going to end up with, let's move this one to the other side, okay, and we will end up with the flux of A that comes from the bulk, from the liquid film to the bulk times the area plus delta the L of the volume is going to be equal to delta of NLI. Okay, I is any element. It can be A, B, or whatever, but in this case we are leaving that's general. And now let's use these ratios here. So we say, okay, let's convert, let's solve for delta of A here, and yeah, we'll end up with the flux from the bulk, AB boiling of the reactor, delta of boiling of the reactor, okay, plus the reaction, and then from this one we are going to solve for the volume of the liquid, which is going to be equal to the hold up of the liquid times the delta of boiling of the reactor. Okay, that's going to be equal to the delta of the flow of the element in general in this element that we have here for the liquid bulk. And finally, we are going to divide this by the volume of the reactor and make it tend to, so let's say all of this is going to be divided by the volume of the reactor, and then let's say that the volume of the reactor tends to 0, meaning we are going to end up with the flux of I from the bulk, AB, volume of the reactor, is cancel out, then same here, cancel out, okay, equal to this one over this one, and tends to 0, we say the derivative of the flow of element I in the liquid over the volume of the reactor, the derivative with respect to that. And now we do the same for the gas. Let's maybe do it just here, the other side, right here, and we'll say that n of the gas that comes in, okay, of course of I that comes in, is equal to the flux of the gas of I from the bulk plus whatever lifts. So here we need to keep in mind that we are assuming that the reaction happens only in the liquid bulk and in the liquid film, so no reaction happens in the gas phase. That's a very common thing. And let's remember that this here, right here, as I said already, this is the flux of component A that comes from B or that goes to B, which is the bulk, and the units of these are mole over meter square per second, and this area is meter square. That's how we get mole over second, which are the units as well of this flow right here. Okay, and finally, this was just a small parenthesis to clear up the units of this, and then we are going to do exactly the same. So we get the derivative of the flow of element I in the gas phase over the derivative with respect, the derivative of this with respect to the volume of the reactor, and it's going to be equal to plus or minus, and I'm going to explain this, Gi of AB, okay, from the bulk, of course. This plus minus because it depends, of course, if you are moving, let's say, component A from so you want to remove this from the gas bulk, so this is going to happen. But if something is dissolving, let's say you produce P, then P is going to move that way. In that case, you're going to have a negative flow, right? Depending on what's your reference. And yeah, I would say that's basically all about these balances that I wanted to show you. And yeah, so there are some theories to model this. So one of the theories, and let's say the very basic one, is the field theory, in which molecular diffusion and a chemical reaction occur simultaneously in the liquid film, and only molecular diffusion occurs in the gas film. And yeah, Fick's law is going to describe the flux in the gas and the liquid film. And yeah, that's basically it. Here at the interface, okay, maybe I'm going to use another figure to explain this. Yeah, so this is what I want to explain, and it's that at the equilibrium, meaning here, right here, let me pick this. So meaning right here, there is an equilibrium between the gas phase and the liquid phase. That's why you can see here some jump, this jump, and it's because they are related, but they have different units. So at the interface, we can say that the interface could be modeled like at this, like the equilibrium state is going to be like this, and of the liquid of I. Okay, so this is the, let's say, what happens at the interface. So the concentration at the gas and the concentration of the liquid in the equilibrium state. So for gases with low solubility, we say that this constant is defined by Henry's law. Okay, and Henry's law only tells us that the pressure times the concentration is going to be equal to the pressure of A, concentration of A, and this is going to be, sorry, this is actually not pressure, but H, right? Let me see. Yeah, exactly. So it's this way. So Henry is going to define this this value of K. Yeah, but we will see this in an example later on. If the fusion resistance doesn't affect the reaction velocity, the flux is simply equal to n of A, element A. We are seeing A now. It's not anymore a general expression. It's going to be equal to NLA. And we will see now some examples of when this happens, sorry. But basically, what we are saying here is that the resistance, the diffusion resistance, doesn't affect the reaction velocity, and yeah, we will have exactly the same equilibrium in this case. So we will say whatever is in the bulk. So we can say in this case Ka, of course, is going to be equal to the concentration of the element A in the gas phase. In the bulk of the gas phase is going to be related to the whatever happens with A in the liquid phase, in the bulk of the liquid phase. And yeah, the flux of this element, so I'm talking about this one, it's going to be determined by fixed law this way. Ga in the bulk is going to be equal to Kga, right? Concentration of Ga in the bulk minus concentration of Ga in the equilibrium, or in the interface. That's the point. Or this, let's say interface. Actually, I'm denoting this by S, in the interface. Okay, so this in this way is more clear. So now we are going to study a little bit the behavior of a slow reaction. And what a slow reaction means, it means that the diffusion resistance in the gas and the liquid films suppress the absorption velocity, so no reaction in the liquid film. Meaning, so you have here liquid bulk and liquid film. As you can see, there is no depletion of this element in the liquid film, meaning this system is going to be kinetic limited. When we say kinetic limited, we are only saying that what limits the performance of the reaction or of the reactor is going to be just the kinetics. So meaning if you even increase this liquid film, you're not going to have any improvement. Okay, so in this case we can tell that N, which means flux of element A from the gas to from the bulk gas, is going to be exactly the same as the flux uh, of A in the liquid bulk, so meaning nothing happens in the liquid film or in the gas film. And then we already said that they are related in this way. We said in equilibrium for the gas is going to be equal to in the equilibrium in the liquid. So remember that this part is talking about the pressure, and I mean the concentration in the gas phase and the concentration in the liquid interface as well. Okay, and we already said that this can be modeled by Fick's law, and we end up with this expression kGa, and yeah, the delta of, or the driving force, which is nothing than this difference of concentrations S, right? And what is this element right here? This is important because this is nothing than the diffusion coefficient over the delta of the gas. So if here we cannot see the gas phase, but basically you have your bulk here, okay, and here you have this gas film, and it's going to be just this distance, this differential, let's say, very small. So this is what is represented by this element here, but this K element here, and we will see that that has a specific name. Yeah, and what else? Then if we say, okay, these two are equal to each other, and we already said this can be modeled this way, so we could model as well this one this way, right? KLA, again we're going to have this one same, but delta of liquid, meaning this delta, okay? And then the driving force, which is going to be from higher concentration to lower concentration, right? And yeah, we will see something about it in the next step. Remember that this means interface and this means bulk, okay? But yeah. And then we can say, okay, if they are equal to each other, so let's equal them, right? We can say, okay, kGa. Yeah, so this is what we get at the end. And we usually know this, we know this as well. We can actually rewrite this one using this expression. Where is it? This expression, right? So we are going to get K, yeah, K times the concentration of in the interface of the liquid phase of A, in the liquid film, sorry. And then we can basically solve for this. That's what we don't know, because I will tell you why we know the others. We can measure the concentration in the gas phase. You simply measure the partial pressure of this element in the gas phase, and with Henry coefficient, with Henry's law, we can have the concentration. And in the liquid phase, this is really easy to measure the concentration in the liquid bulk, but we don't know in the interface. So you can solve this and you will end up with, so we end up with this expression. So you can simply solve for this concentration in the, again, in the interface in the liquid film for the component A. And yeah, so now we are going to plug this expression, this one, into this one. So we are going to plug that here, okay? So we end up with this expression, and then working out this a little bit, we are so as you can see, if you multiply this one at the top and at the bottom for the second element here, the second term, you are going to cancel out this term because you have this element right here as well. Yeah, so we are going to end up no wait, sorry, actually one term is missing here. So as you can see, I have this one here, KGA, sorry about it, and now they actually can be cancelled out, and we are going to end up this really beautiful expression. And at the bottom we have what we call, all of these is what we call actually 1 over K A prime. So this is the overall transport resistance, in which you include 2 terms. If the diffusion resistance in the gas film is negligible, usually this happens for slow reactions, we can neglect this. So here we have the resistance in the liquid film and the resistance in the gas film. So usually for slow reactions, this is just neglected. Yeah, and this is the case for slow reactions. And now let's see what happens with reactions with a finite velocity, meaning that they are not too slow. Yeah, but before going that far, I want to show you this, in which we can see here the very slow reaction, that is the one that we just worked out. Here we have just slow reaction, okay? Here we have fast reaction. Here we have a very fast reaction, in which you can easily see that there is a reaction front right here. And here we have instantaneous reaction, in which even the component A cannot go into the liquid film because it reacts instantaneously right away. It touches the liquid film. And I think that's going to be enough for this video. It's quite long already, and in the next video I'm going to explain what happens when you don't have let's say very slow reactions or instantaneous reactions, and how you relate any reaction with instantaneous reaction. For that we are going to work out in a example, and I hope you enjoyed this session and you learned a lot.